Hi guys. Well, here I am one more time outside to do the lesson. Oh, thank God. Honestly, I hope the last couple of days or the last week, the snow we had, I hope this is it. And it's just warmer and warmer from here on. So I'm out here with the birds, and my neighbors are going to think I'm kind of nuts. But let's do today's lesson. And it's going to be a pretty quick and easy one with some easy formulas, just like everything in the waves unit. So hopefully, you're taking advantage of it. So our next step is to determine how we can calculate the speed of waves. And remember, one of the nice things about the entire waves unit and about the physics of waves is that they only travel at constant speed. There's no accelerations, there's no forces, there's no work that we have to calculate. It's just constant speed. So you can actually write down for speed of a wave, you can write down v equals d divided by t. And you can use this. I mean, every once in a while you get a waves question where they actually do give you distances and times. And if you can go back to the old formula, go ahead. But I put this diagram here of a transverse wave to remind you that one complete wavelength is a full peak and a full trough. Back to equilibrium. Equilibrium's not drawn on here, but if I draw it on here like this, one of the nice things about a wave is this distance here is a real distance, but it's also a wavelength. So if speed is distance divided by time, the nice thing about using waves is we do have a definite distance here that matches one of our wave characteristics, wavelength. So wavelength is an actual physical distance. And the nice thing about that distance is one wavelength, the time that it takes for one wavelength to pass is called period. So we've actually got two wave characteristics that we can use in this formula instead. For distance, we can actually use the wavelength. And for time, I can't really point at it in this diagram, but for time, we can use the period of one wave. So if you sub those two values in, you'll get a modification of the old constant speed formula that will look like this. Speed will be wavelength divided by period. Now that's also a formula that you can use, but that's not usually the way that the formula is written in textbooks. Textbooks take advantage of that fact from last day's work, where period is equal to 1 divided by frequency. So if we stick that in there as a result and sub that in, we'll have speed equals wavelength divided by 1 divided by f. And that's poor format. You never leave fractions inside of fractions when you can help it. Do you remember what to do with this? Do you remember what to do if you have a fraction on the bottom of a fraction? It's actually grade 6 or 7 math. You flip and multiply. Let me write it out like this instead, just to show you that you did do this in elementary school. What you have here is speed is wavelength divided by 1 over f. So what do you do when you divide by a fraction? You flip the fraction and multiply. And yes, you did this a long time ago. So you flip the fraction over and you multiply. You multiply by the reciprocal. And then it's not even a fraction anymore because it's a 1 on the bottom. So a new variation is v equals, and although it's wavelength times frequency, it's usually written on formula sheets as frequency times wavelength. So I'll write it like that just so it's a little bit more recognizable. So this is the constant speed formula for a wave. And what you have to realize is that formula is exactly the same as this formula here from earlier in the course. It's just one quick modification going from the old formula to the newer version of it with wave characteristics in it. So v is still speed. V is speed. It has to be in meters per second. F is frequency. It has to be in hertz. or else things won't work out. And wavelength is, the lambda symbol is wavelength. And that's a regular length like everything else in physics. It has to be in meters. So all we're going to do are two very quick examples to show you how easy this formula is. And then there's 5 homework questions that are actually really just extensions of the examples and extensions of your notes. So first we'll take a look at this question, and pause the video, read the question if you haven't already, because I'm just going to go right into it here. So this question says that you ring this tuning fork and it sends out vibrations. It gives you the wavelength. The wavelength of the vibrations is 275 centimeters. And the tines of this tuning fork, those are the metal prongs of this tuning fork, they vibrate back and forth. Now, it doesn't tell you what the frequency is. It says that it vibrates 375 times in 3 seconds. Calculate the speed of the wave. So, there's really only one way to do this question because it doesn't mention distances and times. It mentions 3 seconds, so I guess there is kind of a time in there. But you would have to use this formula here. Speed equals frequency multiplied by wavelength. But in this question, you're not given frequency yet, so you would have to start with work from last day, where frequency equals the number of cycles divided by time. And in this question, it clearly tells you there are 375 vibrations that are noted in 3 seconds. So divide that on a calculator, you'll get 125, and you can call that hertz because that's standard metric units for frequency. So that's the missing value for this formula. So going back to the previous step, the frequency is 125 hertz, and the wavelength was given in the question, but it's in centimeters, 275. So convert that into meters, 2.75 meters. And do that on a calculator. And it's a little bit too early in the work to make sense of this answer. 343.75 meters per second. But you may want to put a note here for the future. Makes sense. You'll know more about this tomorrow, or rather, I guess on Monday when we do the next day's lesson. This makes sense because what we're going to learn is our next topic is going to be sound waves, and this is a sound question. You're ringing a tuning fork and you can actually hear it. Sound waves always range in the low to mid 300s meters a second. So this actually isn't just a random value. If you had done next week's work already, you would know you did this right as soon as you got 343, because it feels like a sound wave. It feels right. Okay, one more question. Again, pause and read this. And remember what I said. If you're ever given a question where there's a diagram, especially of a transverse wave, I mean, you never really see diagrams of longitudinal waves, but if you see a diagram of a transverse wave, always say to yourself, I have to use the diagram. If you do the question without using the diagram, you're probably doing it wrong. This question says, okay, so we've got a diagram shown below, and this isn't a graph. It's not an X and a Y axis. It's actually measurements up and down and left and right. And the measurements are all in meters. So it doesn't say little m's on here, but you're to assume that these are all meter measurements. And it says here that the diagram that's shown is for 0.8 seconds long of a snapshot. So what you're seeing on the page is 0.8 seconds long. And it wants you to solve for the speed. So I put this question on here because there's actually 2 different ways that you can do this question. You can use the old formula if you want. Speed is distance divided by time. Or you can use the new formula. Speed equals frequency times wavelength. You just have to be really, really careful as to what values you're using for these variables. If you want to do distance divided by time, you can't use period. It actually tells you that the diagram shown on here is for a time of 0.8 seconds, the whole diagram. So if you're going to use that time, use the whole distance. 5, 10, 15, 20, 25, 26, 27, 28.2, let's say. It's about 28.2 meters long, the distance on this diagram, over a time of 0.8 seconds. So if I divide that up, you get 35.25 meters a second. This answer isn't in the low 300s because there's nothing in the question to indicate that it's a sound wave. It just says a wave. So can we get that same answer, or approximately the same, if we do it using the wave formula? Yes. Same steps as before, though. You'll have to do this. You have to calculate frequency first. Frequency equals number of cycles divided by time. And you'll have to count the cycles in this diagram. So crest to crest, we've got 1, 2, and a quarter. That's not a half, that's a quarter. So there's 2.25 cycles shown over a time of 0.8 seconds. So divide that up, and that will give us the frequency, 2.81 hertz. Then you can take that frequency and return to the previous formula. Speed is frequency times wavelength. If the frequency is 2.81 hertz, we just need the wavelength. So back to the diagram, we need one wavelength off this diagram. Wavelengths are crest to crest, peak to peak, however you want to measure them. The easiest, on this diagram, the easiest way to see it is, let's see, there's a node right there. Why don't we do it this way? Because that is right on 3, that dot. Why don't we do it this way? A trough and a peak, and back to the axis again. That's a little bit easier to read because it starts at 3 and it ends at 15.5. So what do we got there? 12.5. 15.5 minus 3, because we're not going to count this bit in the beginning here. One complete wavelength measured across the axis is about 12.5. So a wavelength of 12.5 meters. Multiply these two numbers. The answer won't be exactly the same because of decimals and estimation on the graph, but you get 35.13 meters, which would have been the same answer if the numbers were absolutely exact. So that's it. It's easy work today. There are 5 questions to do. The first 3, questions 1, 2, and 3, are literally just going to take the constant speed formula for a wave and get you to rearrange it. So it's going to get you to solve for speed. Question 2 solves for either frequency or wavelength, and question 3 solves for the other. Very, very simple. It'll take you literally 5 minutes to do those 3 questions, maybe 10. Question 3 on page 391 involves some scientific notation, so I want to make sure that you're practicing that again on your calculator. And question 4 involves some unit conversions, because it mentions kilometers, and we haven't dealt with that on this page. So all 5 of these questions are very, very quick and easy questions that you'll have no trouble with. So my suggestion is don't leave them. Do them as soon as you can, just to get them over with. I'll post full solutions, and that'll end it off for this week. And our next new lesson will be on Monday, and hopefully by Monday, not only will I be sitting out here, but I'll be in shorts and a t-shirt.